A revolution is brewing in the tangled web of human consciousness. Quantum mechanics, the bizarre realm of subatomic particles, may hold the key to unlocking the greatest mystery of all, our own minds. Imagine a world where your thoughts depend on particles smaller than atoms, where your memories are stored in microscopic structures inside brain cells, and your consciousness itself may be the product of quantum processes. This is not science fiction. This is the frontier where physics meets neuroscience, where the nature of reality meets the essence of thought. Scientists are already exploring the possibility that our brains operate on quantum principles, fundamentally changing everything we've assumed and know about the mind. What if our brain is not just a classic computer made up of biological components, but a quantum machine capable of feats far beyond our current understanding? The implications are staggering, affecting every aspect of human existence, from curing neurological disorders to revolutionizing artificial intelligence. How does consciousness emerge from matter? Can quantum effects explain our subjective experience? Are we on the threshold of a new era in neuroscience and technology? To answer these questions, we must journey into the depths of our own minds, exploring a landscape where the boundaries between biology and quantum physics blur. Welcome to the quantum revolution in consciousness. The quest to understand consciousness has preoccupied minds for millennia. Ancient philosophers pondered the nature of the soul, while modern scientists scrutinize brain activity in search of the elusive source of consciousness. Traditional theories of consciousness fall into two main categories: neuroscientific and philosophical. Neuroscientific approaches, in turn, focus on the physical structures and processes of the brain, attempting to identify the neural correlates of consciousness. These theories suggest that consciousness arises from complex interactions between neurons, different brain areas responsible for different aspects of awareness. Global workspace theory, for example, suggests that consciousness arises when information is widely distributed throughout the brain, becoming available to multiple cognitive processes. Philosophical theories, on the other hand, attempt to deal with the subjective nature of experience. The hard problem of consciousness, formulated by philosopher David Chalmers, asks why we have subjective experience at all. Why do we feel conscious rather than just processing information in the dark? And then Sir Roger Penrose, a mathematician and physicist, enters the scene and proposes a radical new approach. Penrose's quantum theory of consciousness suggests that quantum processes in the brain are crucial to the emergence of conscious experience. Penrose argues that classical physics and computation alone cannot explain consciousness. He proposes that quantum effects, particularly quantum gravity, play a role in cognition. According to Penrose, consciousness arises from quantum computations occurring in structures called microtubules within neurons. This is where Stuart Hameroff, an anesthesiologist and consciousness researcher, comes in. Hameroff, in collaboration with Penrose, developed the theory of orchestrated objective reduction, or ORC-OR for short, which has the microtubules at its center. Microtubules are hollow cylindrical structures composed of proteins called tubulins. They are part of the cell's cytoskeleton and play a crucial role in cellular organization and transport. Hameroff believes that these structures are ideal for quantum computing. According to ORC-OR theory, tubulins can exist in quantum superposition states. These quantum states are maintained in microtubules by quantum coherence, allowing for massively parallel computations. When a critical threshold is reached, these quantum states collapse, giving rise to consciousness. In their view, this orchestrated collapse is not random but depends on fundamental properties of the geometry of space-time at the quantum scale. Each collapse represents a moment of conscious experience, and the continuous sequence of these events forms a stream of consciousness. The Penrose-Hameroff theory suggests that the brain operates not just as a classical neural network, but as a hybrid quantum classical system. This could potentially explain phenomena that classical theories struggle with, such as the nature of free will and the binding problem, which is the misunderstanding of how disparate sensory information is combined into a coherent experience. However, the theory remains highly controversial. Many researchers argue that the brain is too warm, wet, and noisy for subtle quantum effects to persist long enough to affect cognition. Critics also point to the lack of direct experimental evidence for quantum processes in neural functions. Despite these problems, the hypothesis of quantum consciousness has inspired new lines of research. Scientists are now investigating quantum effects in biological systems, from photosynthesis to bird navigation. This research may shed light on whether quantum phenomena may actually play a role in information processing in the brain. In the quest to understand consciousness using quantum mechanics, experimental verification is crucial. One pioneering study was conducted deep beneath the Gran Sasso Mountains in Italy, where scientists sought evidence to support a gravity-related model of quantum collapse, a key component of ORC-OR's theory of consciousness. Catalina Cursino, a leading physicist at INFN and Frascati and a member of the Foundational Questions Institute, led this research. Gran Sasso National Laboratory, located 1,500 yards beneath the Italian mountains, provides a unique environment nearly free of cosmic radiation, ideal for sensitive experiments. The experiment used an extremely sensitive germanium detector, surrounded by layers of ultra-pure lead and copper to shield against background radiation. The goal was to detect the spontaneous emission of radiation predicted by the Diasi-Penrose theory, which suggests that the quantum collapse of the wave function is related to gravity and occurs faster in systems with higher mass. After experimenting for 2 months, the team did not observe the predicted spontaneous emission signals. This negative result, published in Nature Physics in 2020, ruled out the simplest version of the Diasi-Penrose model. 2 years later, in Physics of Life reviews, the team reanalyzed the implications of their findings for ORC-OR theory. Despite their efforts, they concluded that most of the scenarios proposed by Penrose and Hameroff are not feasible under the existing experimental constraints. This is the first experimental study of gravity-related quantum collapse in the ORC-OR model of consciousness, which we hope will be followed by many others, Cursino stated. She emphasized that although this experiment rules out some models, the original Penrose collapse model, which does not predict spontaneous emission, remains untested and therefore still plausible. The team is now refining their collapse models and preparing for further testing, keeping the door open for theory. Cursino expresses optimism. It is really exciting to connect what you can do in the laboratory to perhaps the biggest mystery in the universe, consciousness. However, the field of quantum biology continues to discover surprising connections between the microscopic world of quantum mechanics and the macroscopic world of biological systems. Recent research has shed light on a very intriguing phenomenon: ultraviolet superradiation in tryptophan networks. It sounds rather complicated and mysterious, but let's put it all into a nutshell. So what is the study of ultraviolet superradiation from tryptophan meganetworks? Tryptophan, an aromatic amino acid, is ubiquitous in biological systems and plays a critical role in protein structure and function. A study by Babcock published in the Journal of Physical Chemistry B, shows us exactly how tryptophan networks in different biological architectures can exhibit collective quantum optical effects. The researchers analyzed tryptophan networks in several biological structures, including microtubules, centrioles, and neuronal axons. These structures contain huge numbers of tryptophan residues, forming so-called meganetworks. Using advanced computational models, they predicted the occurrence of superradiant states in these networks. Superradiation is a quantum optical phenomenon where multiple emitters act together, resulting in an increased emission rate. In the context of our tryptophan networks, this means that the fluorescence properties of these structures can be dramatically different from what we expect, based on the behavior of individual tryptophans. One of the most striking results of the study was the confirmation of the predicted increase in fluorescence quantum yield in large tryptophan networks. According to their calculations, the quantum yield, which reflects the efficiency of the fluorescence process, should increase significantly as the network size increases from individual tryptophan molecules to complex structures such as microtubules and centrioles. This increase in quantum yield suggests that tryptophan networks in biological structures are not just passive elements, but may play an active role in light absorption, energy transfer, and possibly even information processing in cells. The study focused on ultraviolet excitation, which is particularly relevant to the presence of weak ultraviolet radiation in living systems, often associated with metabolic processes. The researchers hypothesized that super-emitting states in tryptophan networks may contribute to the absorption and transmission of ultraviolet photoexcitations in the oxidative cellular environment. Of particular interest are the results related to microtubule bundles in neuronal axons. The models created by the researchers suggest these structures can exhibit exceptionally strong super-emitting effects, potentially propagating over long distances. This opens up intriguing possibilities for fast information transfer in neural networks. Another important aspect of the study is the concept of cooperative robustness. The researchers found that larger tryptophan networks were more resistant to the effects of disorder, which is ubiquitous in biological systems. This suggests that quantum effects in such networks may persist even under physiological conditions. If these quantum phenomena can indeed work in the warm, humid, and noisy environment of living cells, this opens up a new dimension in our understanding of biological processes. It means that our brains can utilize quantum mechanics, not only under extraordinary conditions, but also as a fundamental part of their everyday functioning. Such robustness under physiological conditions could revolutionize our understanding of information processing, memory storage, and even consciousness itself, potentially leading to breakthroughs in both neuroscience and quantum biology. Understanding quantum consciousness opens up exciting possibilities for the treatment and diagnosis of neurological diseases, such as Alzheimer's disease and dementia. Recent advances in quantum technologies offer promising opportunities for medical applications that could revolutionize the approach of these debilitating diseases. Researchers from the Pritzker School of Molecular Engineering at the University of Chicago, led by Peter Maurer, have been developing state-of-the-art quantum sensors for several years to study complex biological processes inside living cells. These nanoscale sensors, based on diamonds with specific defects, use quantum properties to measure magnetic and electric fields, temperature, and pressure with unprecedented accuracy. One of the most important discoveries in Maurer's research was the ability to insert these quantum sensors into living cells without disrupting their normal functioning. This allows scientists to monitor cellular processes in real time, making it possible to understand the mechanisms of diseases such as Alzheimer's at the molecular level. For example, these sensors can track changes in temperature inside cells, which is important because many chemical reactions, including protein folding, depend on heat. Improper protein folding is a hallmark of neurodegenerative diseases and understanding the conditions that lead to improper protein folding could pave the way for new treatments. In diseases such as Alzheimer's, the body's mechanism for clearing misshapen proteins often fails, leading to a buildup of harmful plaques in the brain. By using quantum sensors to study the heat shock response process by which the body manages the misshapen proteins, researchers hope to develop strategies that would enhance this response, potentially preventing or reversing protein misshaping and plaque formation. Mauer's work is part of a broader effort by the National Science Foundation's Quantum Leap Challenge Institute for Quantum Sensing for Biophysics and Bioengineering. The interdisciplinary initiative aims to apply quantum technologies in biophysics and molecular biology with the ultimate goal of developing new tools for diagnosing and treating various diseases. Quantum sensors can make measurements not available with current technology, enabling early detection of diseases before they manifest clinically. This could lead to revolutionary screening processes for neurodegenerative diseases, enabling earlier intervention and improved patient outcomes. The integration of quantum mechanics into medical diagnostics promises to detect diseases at the earliest stages, potentially changing the landscape of preventative medicine. In parallel, research into the quantum nature of consciousness is shedding light on how our minds work. Quantum mechanics, with its principles of superposition and entanglement, offers a framework for understanding complex cognitive processes and their impairment in diseases such as Alzheimer's. Quantum state reduction, a concept in quantum mechanics, describes how multiple potential states can collapse into a single state, a process analogous to decision-making in the brain. This concept may explain how consciousness arises and how it's affected by neurodegenerative diseases. Because neurons transmit signals, the reduction of quantum states may help map the physical changes that occur during cognitive decline, providing new targets for therapeutic intervention. In addition, studies of how anesthetics affect consciousness are revealing crucial aspects of neurological function. Understanding quantum interactions between anesthetics and neural processes can help develop more effective anesthetics and pain management strategies, improving patient care during medical procedures. The integration of quantum theory into medical research is still in its early stages, but its potential is enormous. As our understanding of quantum consciousness deepens, future research could have a significant impact on the development of artificial intelligence. By studying how quantum processes contribute to human consciousness, we'll be able to develop AI systems that mimic these quantum characteristics, leading to more advanced and potentially conscious machines. This could revolutionize machine learning, allowing AI to perform complex tasks with a level of intuition and adaptability previously thought impossible. In general, the principles of quantum computing inspired by biological systems opens up promising new avenues for technological progress. Future research may reveal how microtubules within neurons perform quantum computation, leading to the development of computational models that exploit these biological quantum effects. These models could significantly improve the efficiency and capabilities of existing quantum computers, finally unlocking their potential for data processing and problem solving. Now, think about this. Understanding consciousness at the quantum level would seriously challenge our notions of individuality and decision-making. And the very idea of potentially creating conscious AI systems raises questions about their rights and the moral implications of their use. Whether or not the following theoretical conclusions turn out to be correct, the journey into quantum realms of consciousness and its medical applications is just beginning. And by continuing to explore these intriguing intersections between quantum mechanics, consciousness, and technology, we're paving the way for revolutionary advances that could change our understanding of the universe and our place in it. The observable universe spans 93 billion light-years, a distance beyond our comprehension. In this cosmic space are more than 2 trillion galaxies, each teeming with billions of stars. The scale of the universe is a marvel, but it is not just its size that fascinates us, it is its complexity. The cosmic web, a network of galaxies and dark matter, forms a structure that resembles a vast, interconnected network. Now let's travel to a place equally complex and impressive, the human brain. Composed of some 86 billion neurons, each neuron in the brain is connected to thousands of other neurons, forming a network of unprecedented complexity. The striking similarities between the cosmic web and neural networks are more than a poetic metaphor. It's a scientific curiosity that's led researchers to explore the quantitative similarities between the two systems. Could it be that the universe with its billions of galaxies is reflected in the complex neural networks of our brains? Are we, in some deep sense, a reflection of the cosmos itself? Could it be that the great design of the universe is reflected in the very essence of our being? Do the laws that govern the stars also govern the complex dance of neurons in our minds? These questions, once the domain of philosophers, are now being explored by scientists who are uncovering a connection that may be the key to understanding not only the universe, but also ourselves. Since the dawn of human consciousness, we've been attracted to patterns. The first humans looked up at the night sky, recognizing constellations and tracing the predictable movement of celestial bodies. They observed the cycles of the moon, the changing seasons, and the complex symmetry of leaves and shells. This innate ability to find patterns in nature is not just curiosity. It's a fundamental aspect of our intelligence, the way we understand the world around us. As we evolved, our understanding of patterns changed. We began to realize that these patterns were not simple coincidences, but were governed by fundamental principles and laws. The ancient Greeks discovered the golden ratio, a mathematic constant found in architecture, art, and even the human body. Mathematicians such as Fibonacci discovered sequences that describe the growth patterns of plants and the spiral motion of galaxies. Natural patterns are not limited to static shapes and numbers. They are dynamic, unfolding in time and space. The branching of a tree, the winding course of a river, the swirling of clouds. Everything is subject to mathematical patterns and fractal geometry. These patterns are self-similar. That is, they look the same at any scale, whether you're looking at a single leaf or an entire forest. In the modern age, our search for patterns has led to revolutionary discoveries. The double helical structure of DNA, the strange world of quantum physics, and the butterfly effect and chaos theory all reveal a universe governed by patterns and laws. These discoveries have not only expanded our understanding of the universe, but have also shaped our technology, medicine, and philosophy. But what drives this relentless search for patterns? Is it simply a survival tool, or does it hint at a deeper connection between us and the cosmos? Could our ability to recognize patterns be a reflection of the inner order of the universe, a cosmic signature imprinted in our very being? In a field of scientific research where the mysteries of the cosmos meet the riddles of the human mind, the research of Franco Vazza and Alberto Folletti serve as a beacon of innovation. Their pioneering work has opened new doors in our understanding of the universe and neural networks, revealing striking similarities that challenge our very perception of reality. At the heart of their research is a question that's intrigued scientists and philosophers alike. Is there a connection between the structure of the universe and the neural networks in our brains? Vazza and Folletti have plunged headlong into exploring this question using cutting-edge technology and mathematical models. Their approach was quite quantitative and focused on the distribution of matter in the cosmic web and the connections between brain neurons. By analyzing large data sets and applying advanced algorithms, they found that the structure of the universe and neural networks obey a similar pattern known as degree distribution. A staggered distribution is a mathematical relationship in which a small number of nodes have many links and most have only a few links. This pattern is found in a variety of natural phenomena, from the internet to social networks. Vasa and Felitti found that the same pattern exists in both the cosmic web and the neural networks of the brain. The implications of this discovery are profound. It suggests that the universe and the human brain share a common architecture, a universal structure that transcends scale and complexity. This connection is not just a poetic metaphor, but a scientific reality, a cosmic signature that resonates in the very fabric of existence. The innovative research of Franco Vasa and Alberto Felitti has ignited a spark in the scientific community. Their discovery of structural similarities between the universe and neural networks has opened new doors, leading to a lively dialogue among experts. Dr. Alberto Felitti commented, "Our study is just the beginning of a longer story. We have shown quantitative similarities between these two systems in structural terms. The architectures of these complex networks look strikingly similar. Combining the efforts of neurobiology and astrophysics can expand our ability to get more results." The significance of their findings goes beyond mere academic curiosity. From understanding dark energy to the development of artificial intelligence, the potential applications are enormous. Dr. Alberto Felitti also added, "If we can demonstrate the similarities between a network such as a neural network and the structure of the universe, we may be able to gain more detailed information about the universe and galaxies. This merging of analysis tools from two different disciplines may help in accelerating the process of developing artificial intelligence or artificial neural networks." But the study has also sparked reactions outside the scientific community. Some have used the results to justify creationist theories or New Age viewpoints. Vasa and Felitti clearly emphasized that their work is based on scientific research and has nothing to do with creationist theories or metaphysics. The future of this research is filled with hope and curiosity. Both researchers express a desire to continue exploring this area by looking deeper into the comparison of these two complex systems. They believe that these results need to be analyzed with more sophisticated tools and that the next steps involve moving to a higher level of complexity comparison. As we delve into the mysteries of the mind and the cosmos, we enter a paradox that has both fascinated and puzzled thinkers for generations. In the vast expanse of the universe, where time and space stretch beyond comprehension, lies a paradox that has baffled philosophers and scientists alike: the paradox of Boltzmann's brain. This paradox is named after 19th century physicist Ludwig Boltzmann, and it delves into the very nature of reality and our understanding of consciousness. Boltzmann's original idea was rooted in statistical mechanics, which studied the probability of random fluctuations in a system. Imagine a universe filled with chaos where particles are in constant motion. In this chaos, there's negligible chance that the particles could randomly line up and form a self-conscious brain. This brain, existing for a fleeting moment, would have thoughts, memories, and perceptions of reality, all without a body or a world to live in. The paradox arises when we take into account the vastness of the universe and an infinite amount of time. Given enough time, the random formation of such a brain becomes not just possible, but inevitable. This leads to the unsettling conclusion that it's more likely for a solitary, self-aware brain to exist in the void than for our entire observed universe to have evolved it as it has. The implications of the Boltzmann brain paradox are profound and disturbing. If the existence of such a brain is more likely than the existence of our universe, what does this say about our reality? Are our perceptions and experiences merely illusions? Are we too just momentary fluctuations of cosmic chaos? The paradox has sparked debate and reflection among philosophers, scientists, and thinkers. Some see it as a challenge to our understanding of probability and the nature of existence. Others see it as a metaphorical exploration of solipsism, the philosophical idea that only the mind of man necessarily exists. From Boltzmann's enigmatic brain paradox, we venture further into the uncharted territories of consciousness. The question that has intrigued scientists and philosophers alike is whether the universe itself can be conscious. The idea that the universe may possess consciousness is not new. This concept has been explored in various philosophical traditions and resonated in some scientific theories. Historically, the concept of a conscious universe has been associated with panpsychism, the philosophical view that all things possess consciousness. This idea has been adopted by some Eastern and Western philosophical traditions, suggesting that consciousness is a fundamental aspect of reality. In the realm of science, theories suggesting that the universe may possess consciousness have emerged from the study of quantum mechanics. Some interpretations of quantum theory suggest that consciousness plays a role in the collapse of the wave function, implying that the observer and the observed are interconnected. Cosmologists and neurobiologists have also explored this concept to understand how consciousness might manifest itself on a cosmic scale. Theories such as Integrated Information Theory, or IIT, suggest that systems with a high degree of complexity and integration may possess consciousness. This leads to the tantalizing possibility that the universe, with its complex web of galaxies and cosmic structures, may have a form of consciousness. The idea of a conscious universe is still a subject of debate and research, yet it's firmly planted in the realm of speculation. Although it encourages us to think about our place in the cosmos and the interconnectedness of all things, the idea enters metaphysical territory and should therefore be treated with caution and critical thinking. Having considered speculative ideas of a conscious universe, we turn our attention to a more grounded and scientific theory, the fundamental theory of consciousness of Donald Goffman. Dr. Donald Goffman, a renowned neuroscientist and philosopher, has devoted his life to unraveling the mysteries of consciousness. His groundbreaking theory seeks to explain one of the most mysterious phenomena in existence, the nature of conscious awareness. Goffman's theory is built on the premise that consciousness is not simply a byproduct of complex computations in the brain. Instead, he argues that consciousness is a fundamental aspect of reality akin to space and time. Drawing on quantum mechanics, neurobiology, and philosophy, Goffman's theory explores the interplay between micro and macro levels of existence. He suggests that consciousness arises from the complex interactions of quantum particles within the brain, governed by principles beyond traditional physics. Goffman's work has led to new experiments and collaborations across scientific disciplines. His theory's been tested through rigorous empirical research using advanced technology to explore the depths of consciousness. Although Goffman's theory has received the support and admiration of many in the scientific community, it has not been without controversy. Critics argue that the theory's reliance on quantum mechanics and its bold claims about the nature of reality require further confirmation and study. Nevertheless, Donald Goffman's fundamental theory of consciousness offers a new view of consciousness that bridges science and philosophy. The connections between the universe and neural networks go beyond mere scientific curiosity. They open the door to deep philosophical reflection and have broader implications for our understanding of existence. These connections invite us to see the universe not as a collection of isolated objects, but as an interconnected network of relationships. They inspire new ways of looking at technology, ethics, and our responsibilities as inhabitants of the cosmos. The study of the universe and consciousness has been a central theme of philosophy for millennia. From ancient Greek thinkers to modern philosophers, the quest to understand reality, existence, and our place in the universe has shaped human thinking. Some see the universe as a deterministic machine, while others take a more mystical view. The connections between the universe and the mind only add a new dimension to this age-old debate. The idea of interconnectedness is not just a scientific observation, it is a call to reflection. It invites us to see ourselves as part of a greater whole, realizing the delicate balance of life and the universe. It forces us to think beyond ourselves and consider the impact of our actions on the wider cosmos. The journey ahead promises exciting discoveries. While the connections between the universe and neural networks are fascinating, it's important to approach them with scientific rigor. Misinterpretations and sensationalism can lead to misunderstandings and detract from the true scientific value of these discoveries. So let our curiosity guide us in our explanation of the cosmos, and let our critical thinking help us stay grounded as we continue to explore the uncharted territories of understanding the universe. Many of us have grown up with the idea that Earth simply revolves around the sun, which stays still in space. But in reality, the big picture is much more complicated and fascinating. As we delve deeper into how Earth actually moves through the galaxy, we'll find that our planet not only revolves around the sun, but is dashing through space at an incredible speed at the same time, along with our entire solar system. But what if we told you that this movement could be connected to some of the universe's greatest mysteries? For instance, scientific hypothesis suggests that Earth's movement through the galaxy may expose us to cosmic rays, which would cause genetic mutations and contribute to the mass extinction of life. Furthermore, changes in our planet's orbit around the sun may affect the environment, which could lead to catastrophic changes, such as another ice age. Understanding how our planet moves through the universe, we can appreciate our place in space more. We may even find clues to answer some of the bigger questions, such as how our galaxy formed and what the future holds for us. For starters, imagine that you're in an airplane that's flying at a constant speed and altitude. While in it, you won't be able to tell how fast you're going or even if you're moving at all. From your point of view, it seems that only the world outside is moving. However, someone on the ground watching a passing aircraft will perceive its movement relative to their own stationary position. This outline, which was first outlined by Galileo Galilei in his 1632 book, The Dialogue Concerning the Two Chief World Systems, to express what we now call Galilean relativity or Galilean invariance. It's the concept that defines the absence of an absolute frame of reference for motion. And even when there are several valid frames of reference, we still need to choose the most relevant one, depending on the situation. So how does this fit in with the idea of Earth's movement and the solar system as a whole? First, we need to determine the observation point. When viewed from within our star system, as we all know, the planets orbit the sun. However, with a broader consideration of things, we can see a completely different picture. The solar system is constantly moving in a spiral through the expanse of our galaxy. One of the best-known examples of relative motion within our solar system is Earth's revolution around the sun. Earth's orbit is not a perfect circle, but rather an ellipse with the sun as one of its foci. That means that at some points in its orbit, Earth is closer to the sun than at others. When Earth is closest to the sun, it is said to be at perihelion, and that the farthest point in its orbit in relation to the sun is known as aphelion. These 2 points occur at regular intervals. Earth reaches perihelion around January 3rd and aphelion around July 4th, which is evident with the seasonal changes of the weather. You know the usual depiction of the solar system, with the sun in the center and the planets revolving around it. Well, that's not a completely accurate representation of the movement within our planetary system. You see, the planets don't just revolve around the sun, but they also pull it in, causing it to shift. For example, the gas giants Jupiter and Saturn have a particularly strong gravitational influence on the sun and Earth, which causes small changes in the shape and orientation of their orbits. When Jupiter and Saturn are even remotely lined up, they have a significant effect on all the bodies in the solar system. This effect is known as the perturbation of the outer planets. Over time, these subtle changes in Earth's orbit can accumulate, leading to long-term changes in the planet's climate and overall environment. These changes are known as Milankovitch cycles. One of the aspects of the Milankovitch cycles is the change in the tilt of the Earth's axis, which shifts from about 22 to 24.5 degrees in a cycle of about 41,000 years. This change in the planet's tilt affects the amount of solar radiation reaching different parts of the Earth's surface, which in turn can affect the timing and intensity of glaciation periods, ice ages. Based on these cycles, some scientists predict that in the relatively near future, a new ice age may begin on Earth, spanning across tens of thousands of years. However, it's important to note that the effects of an anthropogenic climate change are currently suppressing Earth's natural climate cycles, making it difficult to predict the exact timing and intensity of future ice ages. Let's face it, Earth's movement pattern within the solar system is very complex. However, its movement through the galaxy is even more intricate. The Milky Way galaxy is a massive and complex system which includes a vast amount of stars, gas, and dust, spanning across over 100,000 light-years in diameter. One of the most exciting aspects of our galaxy is its rotation. Like a huge spinning windmill, the galaxy's spiral arms trail along as it spins. This rotation makes the stars and gas in the galaxy move in circular orbits around the galactic center. Earth is located in one of the spiral arms of the galaxy, about 25,000 light-years from its center. In the solar system, there are only a few bodies that have to be taken into account in terms of gravity, and the Sun is the dominant celestial body in this gravitational field. In contrast, the Milky Way's gravitational field has no dominant object. Instead, everything revolves within the total gravitational fields of everything else. This makes tracking the motion of the galaxy's components a difficult but rewarding task, allowing us to learn a wealth of information about the complex structure of our galaxy. Just as Earth orbits the Sun revolves around the center of the Milky Way galaxy at a speed of about 143 miles per second, completing one orbit in almost 230 million years. This cosmic journey takes the Sun, and therefore also Earth, through different regions of the galaxy and introduces us to different cosmic environments. Interestingly, the stars in the inner regions of the galaxy move faster than the stars in the outer regions due to the fact that the parts closer to the center of the galaxy have more mass and therefore a stronger gravitational pull. This difference in speed is akin to the way planets closer to the Sun move faster along their orbits than those farther away. Determining the speed of the Sun relative to the center of the galaxy involves searching for new, young stars that have only recently formed and are therefore still in their birth orbit. Next, taking an average of how these stars move relative to us, we can deduct that the Sun is drifting forward at the speed of about 3.1 miles per second, in towards the galactic center at a speed of about 5 miles per second, and up and out of the galactic disk at about 4.4 miles per second. This small, peculiar motion has huge implications for the path that the Sun and solar system take through the galaxy. The orbit of the Sun around the center of the galaxy is not perfectly circular either. Instead, it follows a slightly elliptical path oscillating above and below the galactic plane. It completes a full oscillation approximately once every 60 million years. This movement is influenced by the gravitational pull of other stars, gas clouds, and dark matter in the galaxy. We're currently several dozen light years above the middle plane of the galactic disk, although it's difficult to determine exactly where the center is. Since there is more matter below us than above us, the gravity of the disk slows the upward movement and, in a few million years, will be about 300 light years above the center of the disk before our upward movement slows to a complete halt and we begin to descend. The vertical oscillation is more than just a peculiar phenomenon. Some astronomers support the Shiva hypothesis and believe that it can be directly related to mass extinctions on Earth. Since the center of the disk is a more dangerous place for the solar system due to the higher density of stars and the radiation they emit. The motion of the galaxy's spiral arms is not yet fully studied, but is theorized to be caused by a combination of factors. One of them is the gravity of other galaxies in the local group, the cluster of galaxies that includes the Milky Way. Another factor is the existence of density waves, which are believed to propagate across the galactic disk like ripples in a pond. These waves can force stars and gas in and out of the spiral arms, potentially affecting the environment and living conditions on Earth as we pass through these regions. For example, as the Earth passes through an area of higher density, there may be more cosmic rays and other high-energy particles reaching the surface of our planet. This could have implications for our climate, atmospheric chemistry, and even the evolution of life on Earth. As we discussed previously, the Sun is not stationary. It moves through the Milky Way galaxy, dragging Earth and the other planets along with it. However, the Sun is not the only moving object. All other stars in the galaxy are also in motion. The motion of the stars can be defined in terms of their proper motion, which refers to the star's visible motion across the sky over time. Proper motion is caused by the movement of stars in space relative to the Sun. It's usually measured in arcseconds per year, which is the angular displacement of a star in the sky over the course of a year. The concept of proper motion allows astronomers to track movement of stars over time and study their movement and position relative to each other. This is important because it helps us get a better grasp of the structure and dynamics of the Milky Way. Now, let's take a look at the movement of Earth relative to the nearest stars. Due to Earth's movement around the Sun, the apparent positions of nearby stars in the night sky change slightly over time. This effect is known as parallax. It happens due to the fact that at different times of the year, Earth is in a different position in its orbit, resulting in slightly different viewpoints for nearby stars. The amount of parallax observed for each particular star depends on its distance from Earth. Stars that are closer to Earth will display more parallax than those that are farther away. Astronomers can use the amount of observed parallax to determine the distance to nearby stars, which is an important tool for understanding the size and structure of a galaxy. In addition to parallax, our perception of the night sky is also affected by the proper motion of nearby stars. Over several years or decades, the position of nearby stars can change markedly due to their own movement in space. This means that the constellation patterns we see today will look somewhat different in the future and would have looked somewhat different in the past. The effect of proper motion is especially noticeable for nearby stars that have a large proper motion, or in other words, the fast-moving stars. Now that we have a breathtaking picture of the way our solar system actually moves through the galaxy, one question remains. How do we move through the universe as a whole? As it turns out, the Milky Way is not alone in its travels. Our galaxy is constantly pulled by the gravitational fields of various masses surrounding it. We're currently racing towards the Andromeda Galaxy at the speed of a couple of 100 miles per second. But that's not all. The Milky Way is part of a group of galaxies called the Local Group, which includes more than 54 other galaxies, including our nearest neighbor, the Andromeda Galaxy. The Local Group, along with many other groups and clusters of galaxy, is moving towards a mysterious superdensity in a supercluster of galaxies known as the Great Attractor. The Great Attractor is a region of space about 150 million light-years away, and its gravitational attraction is so strong that it influences the motion of galaxies within hundreds of millions of light-years. As a result, the Local Group is pulled towards the Great Attractor at a speed of about 373 miles per second. However, this movement is still not the last of Earth's movement in the universe. Our entire universe is expanding, and as a result, all the galaxies in it are moving away from each other. This expansion is not a movement in space, but rather a stretching of space itself. The universe is expanding at an accelerating rate, and as a result, the distance between galaxies increases over time. Despite all of this motion, we can still use the cosmic microwave background radiation as a frame of reference for determining our speed relative to the rest of the universe. This radiation, which is the residual heat of the Big Bang, permeates the entire universe and is almost uniform in all directions. By measuring tiny variations in this radiation, scientists have determined that Earth and our entire solar system are moving through the universe at about 229 miles per second relative to the cosmic microwave background radiation. At this point, it's no longer a stunning revelation to anyone that Earth is far from stationary, but rather a tiny but important part of a complex system of celestial movements. The pronounced complexity of the motion of our planet is an impressively complex phenomenon. First, our planet gracefully orbits the radiant sun as it has for billions of years. But that's just the tip of the iceberg. The solar system, which our planet is a part of, also moves through the vast expanses of the Milky Way galaxy, rushing forward at incredible speed and leaving a corkscrew pattern behind it. And that's still not all. The Milky Way is part of a galactic congregation known as the Local Group, which includes a number of nearby galaxies. And together, they perform this cosmic dance as they move toward the mysterious gravitational force known as the Great Attractor. And this tug-of-war causes the Local Group to dash through space at several hundred miles per second. But even that is not the end of the story. The universe itself is expanding, a fact that has been known since Edwin Hubble's groundbreaking discovery in the 1920s. This expansion means the galaxies are moving away from each other at an astonishing rate. In conclusion, Earth is not just a rock flying through space. It's part of a grand scheme, a web of cosmic movements, both intricate and awe-inspiring. We're just a tiny speck of dust in the vastness of this universe. But the movement of our planet is an integral part of the puzzle that is space. By now, we have all become accustomed to the idea that life originated in the ocean. But certain questions still make scientists have fierce arguments with each other. For example, how did life transition from water to dry land? Why would a mass meteorite strike be useful? Is collision with another planet important for the development of life? What did Earth look like throughout the first millions of years of its existence, and what obstacles did it have to face? Some of these questions already have answers, and we will share them with you right now. Life that originated in the water and later made its way to dry land appears as a very plausible theory. After all, the oceans currently cover more than 70% of the Earth and contain many different organisms, some of them studied so little that scientists still continue to discover new species. Once on land, these life forms successfully adapted and evolved to eventually become human. Everyone remembers Darwin's theory, where a fish suddenly decided to spend its vacation on dry land. The modern scientists explained this theory. Fun fact, no matter how many refutations of Darwin's theory you read, scientists take this theory as a starting point just as often. The main question is, what is required for a life to form except for the ocean? To answer this question, we must travel to the distant past of the solar system. The process of creation of the solar system is similar to our neighboring star systems. At some point, about 13.6 billion years ago, the Big Bang happened. According to scientists, it was responsible for creating the universe as we see it in telescopes. And the consequences of this event led to the first chemical elements forming. Hydrogen, which compressed and heated under the pressure of the energy from the explosion, and turned into a new element, helium. We refer to this bunch of compressed hydrogen which turns into helium as a protostar. But the protostars did not stay with us for long. The main benefit of their existence is the emergence of new chemical elements, which became the building blocks for the origin of life. First and foremost, it led to the emergence of ordinary stars. Every star has a life cycle throughout which the star is akin to a factory. Something is burning, there is some smoke, and streams of resources are flowing through to produce something. Simultaneously, all of these processes affect the ecology and environment. So our sun, like any other star, does the same thing, but on a cosmic scale. And then the life of a star factory is pretty prosaic. It either expands to a supernova or transforms into a red giant or a dark dwarf, followed by attenuation and death. Alternatively, a star can turn into a black hole. We know for sure that the sun will become a red giant, eventually expanding to encompass nearby planets, including us. However, we still have 5.5 billion years before that happens, so we'll have enough time to finish watching our favorite TV shows. What is so special about our solar system? Scientists theorize that the sun was created by a supernova being destroyed not far from the future solar system. Thus, our star, having arisen from compressed clouds of gases, will have eventually absorbed such a high amount of matter due to gravity that it will be enough not only for its existence, but also for the creation of the entire solar system. Everything that was not a part of the new star began to revolve around it, flattening and acquiring the shape of a disk. That's a huge amount of matter. Some of it will be lucky to become a planet, and some will leave the sun's immediate orbit to become a comet or a dwarf planet. The future cradle of humankind came to existence somewhere around here. At the start of its life, Earth was something like a stew of lava, rocks in a liquid form, and crazy mixtures of gases released during the melting process. Near Earth's surface, the temperature exceeded 1,200 degrees. There was no air, only carbon dioxide, nitrogen, and steam. Moreover, the planet was being continuously bombarded by comets and meteorites, some attracted by the planet itself and some attracted by the sun. This is where the water particles that eventually land on Earth come from. But at this point, there is no talk of any life. Earth receives the most powerful blow in its history, but also the most useful, as it turned out later. A planet the size of Mars, which was later named Theia by the scientist, crashes into us. The result of this collision is the formation of the current shape and size of Earth. But even more importantly, the fragments form into our satellite, the Moon. Initially, it was much closer to us, 13.6 thousand miles. This will have an effect later on. The importance of the moon will become more evident as Earth cools down. Over time, Earth's temperature began to lower, which led to Earth's crust forming, a thick layer of everything that our planet collected due to gravity as it was forming. And after the cooling process, only the very core of the planet, molten iron, remained hot and liquid. It is the activity within the core that creates the magnetic field around Earth and keeps it at its stable moving pace, both around its own axis and around the Sun. As the temperature kept dropping, the planet experienced its first rainfall. Around 3.8 billion years ago, it was subjected to a meteor shower, the remnants from the formation of the solar system bombarding Earth. But inside these bombs, there was also something useful, namely water. Those are not yet the kind of rains we're used to. At the time, the speed of Earth's rotation was so high that a day only lasted 6 hours. However, thanks to that very useful rain, the first ocean is formed on Earth. Meteor showers lasted 20 million years, so the low water content in each individual meteorite was not a problem. Quantity led to quality. At this stage in Earth's development, scientists had a question: where did water actually come from? There are two theories regarding this. Some believe that all the water was brought to us by meteorites. A second theory suggests that there was already water on Earth. The argument was solved by time and new discoveries. Both theories turned out to be right and wrong at the same time. Studying the soil from the moon's surface revealed that the then young and active sun burned everything that could evaporate from the planets, including water and gases. And so the scientists still cannot definitively say whether there is more water of meteoric or terrestrial origin present on Earth. And most likely, they will never be able to answer that question. But the main thing is that the collision of Earth and Theia became a catalyst for the beginning of the cooling process of the planets, and subsequently, the formation of Earth's atmosphere, which would serve to protect it from the sun. The existence of the atmosphere became the shield that maintains everything needed to create life and doesn't let anything harmful in. How did the atmosphere form? Earth has cooled down, but the volcanoes are still active. Due to this volcanic activity, water evaporates, turning into clouds, which then turn into rain. For millions of years, rains fall to Earth's surface, pooling into lakes, then seas and oceans. And this worldwide ocean was very stormy. You know how the moon influenced the tide. At the time, the moon was much closer, and its rotation around Earth caused such powerful ocean storms we could hardly imagine the scale. Some waves reached no less than 1,000 feet in height. Meanwhile, the winds on Earth were nearly as fast as the speed of sound. And so the ocean is raging, the storm is at full swing. Where is life? Contemporary theories generally agree on one thing. Back then, Earth's oceans were an ideal place for the emergence of life. But there are several problems. The main question is, how did organic matter, that is, chemical elements that are the building blocks of life, come to exist under these conditions? Let's break it down. Water in Earth's atmosphere at the time, specifically nitrogen, hydrogen, and carbon dioxide, are elements from the inanimate part of the chemical elements, the so-called inorganic chemical elements. To answer this, let's look at the theory that was developed by Oparin, an academic from the USSR in 1924, as well as a similar theory put forward by a biochemist from the UK named Haldane in 1938. In essence, these theories are simple. The ocean of that time was constantly replenished with organic substances from the atmosphere, which was constantly struck by lightning thanks to the endless storm of that period. It was under the influence of these electrical charges that these elements in the atmosphere turned from inanimate, inorganic, into living, organic, and fell into the water. Once they were in the water, the particles slowly gathered together and formed a broth of organic matter, which would subsequently develop into living organisms. The way these particles behave was similar to the behavior of cells. They can grow, divide, and absorb other chemical elements. But the truth is, the organic matter only acts as the building blocks of the body. Creating life itself requires a team of workers and a foreman to bring everything together. The foramen of our cells is our DNA, an entire library of how everything works, from reproduction to building complex structures from sets of cells. The workers performing the task are RNA. The Oparin-Haldane theory is similar to the story about Frankenstein's monster, whose inanimate matter was also brought to life by a lightning strike. The main thing that we know is that life arose somewhere in the ocean and for 300 million years existed in the form of single-celled organisms. They were not particularly in a hurry to turn into people, were they? But to be frank, the conditions of the ancient Earth would not have given something more complex a chance to develop. The single-celled organisms that existed then were prokaryotes. The main difference between them and us is that their organism consisted of one cell without a protective membrane, and in most cases without a nucleus. A good example of the currently existing prokaryotes is bacteria. On Earth, first, oxygen came to exist in sufficient quantities to begin to form the atmosphere in which we now live. And then, within a billion years, somewhere between 3.5 and 2.5 billion years ago, a new miracle took place. Single-celled organisms, even in such a literally toxic atmosphere, have learned to use the energy of light to convert water, carbon dioxide, and solar energy into their first food, glucose. The byproduct of the process produced even more oxygen. We refer to this miracle as photosynthesis. After the cooling of the Earth and the formation of the ocean, a terrible thing happened. 2 ice ages took place. The first, known as the Pongola Glaciation, lasted 500 million years. The second, the Huronian Ice Age, was slightly shorter, but it almost exterminated life on Earth. The Huron Glaciation lasted 300 million years. It was caused by an oxygen catastrophe. It happened due to the fact that thanks to photosynthesis, unicellular organisms began to release so much oxygen that it led to the extinction of all unicellular organisms that existed without oxygen. And so aerobic organisms, the organisms that need oxygen to exist, became dominant life forms on the planet. Next, prokaryotes continued to evolve into eukaryotes, both our closest and the most ancient ancestors in terms of cell structure. Eukaryotes were able to compete, absorb, and destroy their own kind. They used solar energy as the main source of life and were also able to reproduce. Eukaryotes gradually moved closer to dry land, formed by volcanic activity, producing more and more oxygen along the way. In the shallow water, they united to form the prototype of underwater trees, stromatolites. First, they became red algae, with their key feature being the ability to reproduce sexually. This skill will give an impetus to evolution, resulting in the next prototype of modern nature, mushrooms that grow on land. 540 million years ago, the Cambrian explosion occurred, characterized by the dramatic increase in the number of living organisms. This event prompted the emergence of future animals, plankton, and calcimicrobes. 70 to 80 million years later, another rapid leap in evolution takes place when most of the species known to us today come to existence. The first animals to set foot on dry land were arthropods. At first, they simply roamed the land in search of more satiating food than algae and plankton, but then they never went back into the water. According to scientists, one of the most interesting species that transitioned from life in water to life on land is the Tiktaalik fish. Its limbs were like paws, which made it possible for them to move out of the water. For 360 million years, plants, having learned to reproduce by seeds, spread across the land and more. The insects will soon fly into the air. Amphibians, having evolved into four-legged tetrapods, remain on dry land, having learned to hide their eggs from predators and eat a variety of foods. In the future, these animals branch out into several species, giving rise to lizards, birds, artiodactyls, and primates. Yet another blow awaited them: the Permian extinction, which killed 90% of water-dwelling species but left many species alive on dry land. It took the ecology about 90 million years to recover. Then there was the era of the dinosaurs that went extinct due to a meteorite impact, but the birds and half of the other species survived. Life has finally conquered the land. Let's sum it up. Earth has a unique combination of factors contributing to the origin of life. The question about the origin of life remains unanswered, but we have some intriguing clues. Water and the world's oceans are the main source of these answers, but not the only source. Our oceans are unique. They are a result of Earth's planetary evolution. We live in a beautiful time when discoveries related to the transformation of inanimate elements into the living matter are closer than ever. We even envy ourselves a little. After all, the secret of life may soon be revealed.